Sure. Yeah. So let me know when I should start. Okay.
Sure, sir. Sure, sir. Thank you, sir.
Professor Rao, am I audible? I put on my headphones. Am I audible?
Yes, sir. It's audible, sir.
Yes, sir. Yes, sir. You're audible, sir.
Okay, thank you. Yeah, so let me know when to start.
Yes, sir. In few minutes, sir. 2-3 minutes.
Oh, sure, of course.
Thank you. Thank you. Dhanraj?
Sir.
Yeah,
Sir.
we can start. I think.
Yes, sir. We can start the session, sir. Yes. Mukul, sir.
So should I start?
Yeah, good morning. Sir,
Yeah.
so just a minute.
Sure.
Good morning, all. I would like to request Professor Sainam, one of the faculty members of our department, to start with the proceedings. Sai, sir? Sai, sir, can you hear me?
Yes, sir, I can hear you.
Yeah.
Yeah. Good morning, honorable guests and most valued participants. It's my tremendous honor to introduce our speaker for today's FTP on quantum computing. We are indeed privileged to have noted educationist and eminent researcher Sri Debajyoti Bera as our resource person. Sri Debajyoti Bera is currently an assistant professor in IIIT Delhi. He received his PhD in computer science from Boston University in 2010 and BTech in computer science and engineering from IIT Kanpur in 2002. He is currently involved in active research on topics in quantum complexity, graph algorithms, and privacy issues in online services. His usual areas of research interest spans quantum computing, algorithms, theoretical aspects of security, and privacy and algorithm challenges in other domains like database, networking, etc. Apart from theoretical computer science, he is also interested in open source development and computer system. When not engaged in academic thoughts, he prefers to engage in photography, music, and reading. So it's a proud privilege to have him as speaker for today. Sri Bera sir, on behalf of management, principal, HOD, and all the participants, I request you to start the session. Thank you, everyone.
Thank you for that nice introduction, and thank you for inviting me. So the plan today is to sort of give us very simplified view of quantum computing as a subject. So I teach this subject, and this requires a bit of preparation to understand things. So the first few lectures in a quantum computing course are usually spent in preparing the mathematical backgrounds. But so what I'll try to do is I'll try to sort of give you a glimpse of what sort of tools are required and what sort of things that you can do if you sort of go deeper, if you are interested. So the objective, so probably I'm just hoping that some of you will leave with the takeaway message that if you want to further pursue this field, then what are the tools and techniques that you need to master, and should you pursue, what sort of results or what sort of emerging things can you participate in? Okay, so let's start with the presentation. So right. Okay. So before I start with formal quantum computing and quantum algorithms, I should tell you a little bit about what happens if we do just normal plain old classical computing with random bits. Okay. So random bits, as in, so just think of algorithms that tosses random coins. Okay. So some of you may be familiar with things like quicksort, Monte Carlo sampling. And let me tell you that classical randomized algorithms are already very, very efficient. And not only in the real ones in a practical sense, but also theoretically. For example, this is a problem that all of you should be familiar with, the 3-SAT problem. It's an NP complete problem. And the satisfiability finding the satisfiability, solving the satisfiability problem for a 3-SAT Boolean formula, that the brute force algorithm takes 2 to the power n time. So for example, if it has where n is the number of variables, so if you have formulas with 100 variables, then the time you will require is roughly of the order of 2 to the power 100, which is more than the number of particles in the universe. So but such Boolean formulas appear routinely in industry, where they have to solve Boolean formula over thousands of variables, and there are very, very efficient solvers for handling them. And as you can see that there is a clever deterministic algorithm that uses something like 1.44 to the power n, but if you can, it is possible to randomize that algorithm, and you can get an even better complexity, 1.321 to the power n. Okay, so if you want to draw a graph, then 2 to the power n is something like this, 1.43 to the power n is something like this, 1.3 to the power n is something like this. Okay, so the complexity is, I mean, even though it's 2 and 1.4 and 1.3 are not very different, but when you exponentiate them, when you raise them to the power of n, the complexities that you get are really remarkably different. Okay, so keep this thing in mind that randomized algorithms already are extremely efficient. I mean, classical non-randomized things are already very, very efficient. We can solve enormous amount of, we can do complete gene sequencing. So such is the power, computing power, and on top of it, if you add randomization, then it has the potential to improve more. So in this light, keeping this in mind, we want to understand what does quantum computing bring to us. And for that, we need to understand a little bit about quantum computing. So the basic of quantum computing are something known as qubits. So let's make the transition from bits to qubits. Okay, so on the left you see two pictures. One is that of a spin of an electron. So you can think of a spin as I mean, these are all sort of, it's not right to think of it as spinning as something like spinning like this or like that, but towards the right, clockwise or anti-clockwise, but you can think of it like that. So electron or a ball or a particle can spin in two different ways, clockwise or anti-clockwise. So it is possible to therefore encode the value 0 and 1 in these spins. Spinning in the anti-clockwise direction, I'll say that it is storing the value 0, and if it is spinning in the clockwise direction, then I'll say that it is storing the value 1. And so that is one way one could think of implementing 0-1 binary bits using spins. There's another way that is very popular, that is using photons. So on the bottom picture, you see that you have a photon, and the photon lands on you have a photon source, and there is a polarizing beam splitter or otherwise known as a half mirror that's in front of it. So what happens when light falls on the half mirror? So the light sort of randomly either passes through or well, this is a different thing. Okay, so there is something known as a polarization, but so forget this term. Let's think of it as a half mirror. For some reason, it is not writing very nicely. Let's see. Okay, so I'll try to. Okay, so think of it as a half mirror. So if it is a half mirror, then the light can either pass through or it gets reflected. So what happens is that when a photon falls on the half mirror, half the photon, suppose there's only one photon then falling on the half mirror, it will either go straight, or it will reflect. So when it reflects, then right, so there is an equal chance of it's reflecting, and we can encode 0 and 1 in the following manner. Then if we say that if the photon is traveling in the forward direction, then it is encoding the value 0. If it is reflected, if it is moving in the vertical direction, then it is encoding the value of 1. So you can see that these are all different ways to encode zeros and ones. Okay, the catch is the following, that all of these electrons, photons, these are all quantum mechanical objects, which means there are which means that there are these the actual spin of a photon, spin of an electron, or the actual path of a photon, unless you observe which path it is taking or what is the actual spin, it is sort of non-deterministic, in a sense that you wouldn't know whether the spin is anti-clockwise or clockwise, or for the photon example, you wouldn't know whether it is moving in the horizontal direction or the vertical direction. And that is, so in a way, so what I'm trying to tell you is that probability is inherently inherent in quantum mechanical properties. So unlike classical domain, where we need an additional random coin and we need to toss the random coin to get general probability, here probability is inherent. These particles are by their nature probabilistic, and that is what we try to leverage in quantum computing. Essentially, it's a sort of version of randomized algorithm, randomized computation, just with some different rules of randomization, but so the basic ideas remain the same. So it's probability calculations all over again. Okay, so given that context, so what my plan is, depending on the time that I get, So I'll try to recap the basic principles of quantum computing. I think yesterday you heard Professor Jayakumar. He tried to give you an overview. I'll also, but many of you probably are hearing this for the first time. So I think it doesn't hurt to listen to something twice. So I'll give you my way of understanding the basic principles of quantum computing in a very simplified manner. Then I'll tell you how to roughly design quantum algorithm, at least some ways of designing them. And then I will end the talk with discussing some of the really cutting edge emerging techniques. So you will see a bit of details, slight bit of details in the part 1, but on 2 and 3, I will gloss over. I will only give you the high level overview, because starting at 1, coming to 2 and 3 requires significant more mathematical jugglery that I'll not be able to cover in just 1.5 hours or whatever time is left. Okay, so let's start with a single qubit. Okay, so a single qubit is, let me see if I can make this full screen. Yes, I can make this full screen. Okay, so one qubit is a basic data type. So I will try to relate quantum computing with classical normal programming things with you. Okay, so a single qubit is a basic data type. Modern days we deal with the basic data types are something like int, char, float, and things like this. But those of you who are old enough would remember that at some point we used to talk about bits and bytes as basic data types. So we are right now in quantum computing. We are right now at somewhere at that stage. And so a basic data type is going to be one qubit. One qubit is the equivalent of 1 bit. Okay, a quantum version of 1 bit. So one qubit can store two values, either 0 or 1. So we would say that a qubit is in the state 0 or state 1. Okay, remember a class when we say that I have a variable of bit. Let's say I have a bit b. So if you can see the left box, I have written a small sort of pseudo code there. I have defined a variable var b. This is just normal classical programming, Python, something like this. Okay, so here even though we use a phrase that b equals to 0, what we really mean is that b is storing something that represents the value 0. So the state of b is that of state 0 is the more right way of doing it. Classical computers typically use voltages to denote states. So 0 is not really a value. It is just saying that the voltage for a particular register is so and so. Okay. So just keep this sort of language in mind, that state 0 means that the variable is representing a value 0. So one qubit can store two values, or rather one qubit, the way we will say it is one qubit can be in two states, state 0 or state 1. That's the sort of the first where we start. Okay, and is usually implemented as one way to implement it as a spin of an electron. Though the modern quantum computers do not use that, they use something known as the direction of current in a Josephson junction. Okay, so let's first look at the behavior of a random bit. Okay, so look at the box, the code in the box. So I have a variable b which I initialize to 0, and then I set it to a random number. Okay, so the question I want to ask is that after line number 2, what is the value of b? What is the state of b? So let's look at line number 3 and line number 4. So in line number 3, I say if b equals to 0, I print 0, and in line number 4, I say if b equals to 1, then I print 1. So now, suppose I run the code, and then I observe 0, then I know for sure that b must have been 0. Or if I see 1, then I know for sure that b must have been 1. And why is this the case? Because when I execute line 2, when I say that b is assigned 0 or 1, I'm really choosing between one of the two universes. I'm either in the b equal to 0 universe or b equals to 1 universe, right? These are completely mutually exclusive. They're disjoint universe, disjoint possibilities. Either it is b equal to 0 or it is b equals to 1. It just cannot be something in the middle, right? Okay, and so that's why in the b equals to 0 path, my program will output 0, will only print 0. In the b equals to 1 path, the program is only going to output 1. Okay, so which means that if I observe the output of the program, then I can uniquely determine that which world I am in. I'm going to be equal to 0 world or be equal to 1 world, right? Okay, so that's how a classical random bit behaves. Now let's see how a qubit behaves. So let's look at the second box. So I have a qubit b, which I initialize to the state 0. I use that bar and the angle just to indicate that this 0 is indicating the state 0, and this is the this is the notation that was given by Paul Dirac and has sort of stayed on. It sort of indicates that this is a qubit and not a regular bit. Okay, so I have a qubit B which is in the state 0, and I apply the some operation H, which is similar to the random operation that I was doing for classical. Okay, and then once again I measure I observe what is the value of B, and if I see 0, I print 0. If I see 1, I print 1. The question once again is that what is the state of B at after the second line, second statement. Okay, it so turns out, and you will understand it better as I move in the presentation. It so turns out that B equals to 0 and B equals to 1, these two possibilities are no more disjoint. Okay, when I randomize, B can now be both 0 and 1. It is no more an OR phenomena. It is something like an AND phenomena. This is a bit of counterintuitive. How can something, I mean, no matter whether it is, doesn't really matter whether it is an electron, photon, or whatever, or a cup, or a tea, or a teapot, something. How can it be two things at the same time? But that is sort of where intuition breaks down when we start entering quantum mechanics, and it's better to rely on mathematics there and not rely on intuition, because at quantum level, most of the times there are fancy stories about quantum mechanics. Those who follow popular science must have read things like Schrodinger's cat and things like this, where our popular intuition breaks down. And it's best to rely on intuition and and why should you trust your intuition? Because experiments have been designed which sort of have established that the theory that have been developed based on the mathematics that somehow are able to explain the phenomena that we are observing. Okay, so think of the behavior of the qubit. It is both state 0 and 1 at the same time. So it is not an OR phenomena. It is not that the qubit is either in this or that, but is roughly qubit is in both this and that. Okay, and if I only observe the state, the output, whatever is printed, it is a real challenge to figure out what the actual state of B is. That's something known as quantum tomography. It's not a very obvious thing to do, unlike what we were doing in classical. Okay, so let's look at the first interesting one qubit state. Okay, so the thing that you see in red is how I represent a one qubit state. So I'm going to parse the thing to you. So on the left you see psi, which is enclosed in that bar psi bracket thing. So this is how I will denote a qubit. Always, just to show you that this is different from a classical entity. It's a quantum entity. It's a so it's just a notation. Okay, so left hand side, that thing is a state psi, is state of a single qubit. Then I have this 1 by root 2. Once again, a qubit in the state 0 plus I by root 2, a qubit in the state 1. So this 1 by root 2 and I by root 2, they are known as amplitudes. And this plus is a vector addition. So you must be wondering where is something like, what is the vector coming from in this picture here? And the state 0 is a shorthand for the vector 1, 0. And the state 1 is a shorthand for the vector 0, 1. Okay, so now let me just slightly move ahead, move to the right. So if you now see what psi is, so if you replace that the state 0 by the vector 1, 0 and 1 by the vector 0, 1, you see that the psi becomes a vector 1 by root 2, a column vector which is 1 by root 2 and I by root 2. I thought I would be able to write, but for some reason, okay, I can still.
Sir, figure is selected. Maybe you deselected.
Once again,
at the top, figure is selected. The circle and the square is there. No? At the top left, where the settings are there. Settings.
No. That is no. So that's different. So it is something. It is occasionally giving a problem. It seems now I can write. See, now I can again. Yes. Yeah, it is. Yes, at some point it is not allowing me to write. That's the problem. I'll see if I can write in some other place. Yes, it is giving me some headache. Okay, I'll try to avoid writing. Okay, so I'll get a column vector which has, I'll get a column vector which has 1 by root 2 at the first entry and I by root 2 at the second entry. Okay, so a state, a mathematical representation of a state is a vector in a two-dimensional vector space over complex numbers. Okay. And that is what is, so if you start reading quantum computing, you will hear the word, if you read the word Hilbert space, and that is what we mean by Hilbert space, a vector space over complex numbers. Okay. So suddenly now a qubit, which was supposed to be an equivalent of a bit, is becoming a vector. What does that mean? Just stay put. Hopefully within 10 minutes you will get a clearer idea what am I going to do with these vectors. Okay, so for now just stay with me and just try to understand, just try to sort of keep this picture in mind, that a state of a vector can be mathematically represented as a complex vector, a two-dimensional. If it's a 1 qubit, then its state is a two-dimensional column vector, complex column vector, and if it is a 2 qubit, then it would be a 4-dimensional complex column vector. If it is a 3 qubit, it would be a 8-dimensional. So if it is a n qubit, it will be a 2 to the power n dimensional complex column vector. Okay. So 0 is a complex column. 0 is a vector. 1 is a vector. So I multiply them by the scalars 1 by root 2 and I by root 2. Then I add them up. So now sort of the right hand side sort of makes sense. Everything is a vector. I can add vectors. I can multiply vectors by scalars, and so I get the left hand side. Okay, so let's see what we can do with the vectors. Okay, so if you're wondering why are we suddenly treating variables as, I mean, we started with the idea that qubits will be storing some value, will be in some state which will be denoting some value 0 and 1. You may be wondering why suddenly we want to treat them as vectors. So I want to tell you that vectors are not a very bad way often to indicate, treat variables. In fact, the classical randomized algorithms that can be analyzed using that can be analyzed using random variables, and these random variables can be further represented using stochastic vectors or probability vectors. So just for an example, say we have a random bit b which is either 0 or 1 with equal probability. Then one way to represent b would be as a column vector with the value half and half. This half and halves, this half column vector can be written as further half times this column vector 1 0 plus half times this column vector 0 1, which shows, and as before I will represent the 1 0 column vector. I will use a 1 0 column vector to represent that the b is equal to 0, and I will use the 0 1 column vector to represent that b equals to 1. So therefore this half column vector is a combination of these two column vectors with coefficients half. Okay, so this is one way to represent a random bit that is with probability half. So because you can see on the right hand side with sort of coefficient half, I am representing 0, and with coefficient representing 1. Okay, so that is another way of representing even classical random values using column vectors. And in fact, if you ever have done sort of Markov chain or stochastic processes, then you would probably, you must have, or you would see, you deal with these sort of column vectors, stochastic vectors to analyze your algorithms, analyze your processes. Okay, so these are not a very uncommon thing to do. It's not done usually, but sort of certain as certain subtopics of classical algorithms also used vectors to represent variables, states of variables. So I mean, so now why did I choose this 1 0 and 0 1 column vectors to denote the right hand side? Because it turns out that 1 0 form a basis vector of two-dimensional real vector space. Okay, so there are other bases as well. So for example, another basis for, instead of 1 0 0 1, the another basis could be 1/3 2/3 and 2/3 1/3, which you see slightly below. Okay, and I can once again represent half this column vector in terms of this new basis vectors 1/3 2/3 and 2/3 1/3, right? And I have done the calculations for you. You can verify later that this is going to be once again a equal combination of these two column vectors, except that it is not immediately clear what to do with these sort of representation. The earlier representation is clear, the one on the top, where I'm representing half in terms of 1 0 and 0 1 column vectors, that says that 1 0, so 1 0 represents b equals to 0, 0 1 represents b equals to 1. So it says that okay, this is a column, this is a combination, equal combination of b equals to 0 and b equals to 1. Whereas in the second one, it's not immediately clear this what does this 1/3 2/3 represent, what does this 2/3 1/3 represent. It's not immediately clear what to do here, but nevertheless, I wanted to put this up because this is something we will do for quantum, and there it will make sense. But so the takeaway message from this slide is that algorithms using random bits can be analyzed using stochastic vectors. And what are stochastic vectors? These are unit vectors using L1 norm. So you add the values up, it should add up to 1. That's what I mean by L1 norm over real numbers. Okay. So now let's get back to our vector representation for quantum qubit state. Okay. So zero, the state 0. I had used the column vector 1 0 to represent the state 0, and I had used the column vector 0 1 to represent the state 1, and I have right, there is a slight mistake here. Okay, there is a slight made while typing. So imagine that the state psi, the amplitude in front of R1, the state 1 is not I by root 2, but imagine it is 1 by root 2. So then the calculation below will actually going to be correct. Okay. So yes. Yeah. Is there any question? Okay. Okay. So okay. So even just like we did above, even for so there are other basis vectors apart from 1 0 and 0 1. So suppose we take another basis vector. So I take this basis vector, that is you see below, 1 by root 2 1 by root 2, these two column vectors, 1 by root 2 1 by root 2 and 1 by root 2 minus 1 by root 2. These column vectors appear so popularly and so frequently in quantum algorithm that there are even some small symbols for it. We use the state plus and the state minus to denote them. So plus denotes the column vector 1 by root 2 and 1 by root 2. Minus denotes the column vector 1 by root 2 and minus 1 by root 2. So now I can represent the state above when you replace that I by 1, that state above using this plus and minus column vectors. Okay, and the amplitudes will be 1 plus I by 2 and 1 minus I by 2. Once again, it is not immediately clear what do we gain by writing psi in terms of plus and minus, but we will come there. But so what I wanted to, so the takeaway slide from here is that algorithms using qubits can be analyzed once again using unit vectors, but over L2 norm and over complex numbers. L2 norm basically means that you would take the entries, you would take their absolute values, and you will square them up and add them up, and you take a square root. So L2, it is unit vectors over L2 norm means if you the sum of the squares of the absolute values add up to 1, and the variables can be complex numbers. Okay. So so just remember this one, and then we'll go ahead with this. Okay. So far this was about the mathematical representation of a qubit, how I represent. But let me come back to the original question, the bothering question that is probably bothering some of you at least, that what do I do with this? I mean, what is the value? Because we started with the analogy that I have a variable, a single bit variable, and then I said, okay, qubit can are similar to it. So what is the value of a, I mean, a vector is not something that we are, when we program, we don't use a vector, right? We use variables. Ints. In this case, I'm really working on a very primitive level computer, so I'm dealing with bits. So what is the value of a qubit? So these vectors are also known as the state vectors. So what is the value of a qubit, or what is the value of a state vector? So if you see the flow diagram on the right side, so these are standard flow diagrams that we use for representing classical algorithms. So we say that if x is something, so what does it mean? That means that if the value of x is something, or if x is in this particular state, so we need to, so let's understand what do I mean by a value. Okay, so now so I want to, okay, so now I want to draw an analogy. So imagine I have a sort of a line segment. Okay, so forget what I was talking about, this whole quantum business. Imagine I have a line segment, and imagine I have a ruler a ruler which has both the inch measurements, the inch marks on one side and the centimeter marks on the other side. Okay, so if I and imagine that there are no sort of the finer mark, there are no millimeter mark, there are no this marks inside the inches. We have only 1 inch, 2 inch, 3 inch, 4 inch, and we have only 1 centimeter, 2 centimeter, only the sort of the inch and centimeter level marks. Now, if I measure that line segment, then if I give you that scale, the ruler, and I ask you the measurement, you would definitely have to ask me that what do I measure this in? Should I measure it using the inch measurement, or should I measure it using the centimeter measurement? And the values that I will get are different. Okay, the same physical quantity, the same line segment can be measured in two different ways. So it's something similar here. I can write that state, the column vector 1 by root 2, 1 by root 2 in these two bases, in the plus minus, in the 0 1 basis, which is that representing that column vector using the states 0 and states 1. Remember that state 0 is the column vector 1 0 and state 1 is the column vector 0 1. So I can represent it using that, or I can represent the state using the plus minus vectors. Plus minus were defined in that manner, 1 by root 2, 1 by root 2, and minus was defined as 1 by root 2 and minus 1 by root 2. So now the same column vector, same state, I can write it in two different manners. And now, if you see a little bit below, suppose I measure the psi. Suppose I measure the psi in the 0 1 basis, what will happen is I will observe. So this was 0. Okay, this occasionally gives me a headache. Okay, so if I observe measured in the 0 1 basis, any question, anything there? So if I measure this in the 0 1 basis, then I will observe the state 0 with probability 1 by root 2 square. How did I get that 1 by root 2? This was the coefficient of the amplitude in front of the state 0. And if so I may observe the state 0 with probability 1 by root 2 square, which is 1 by half, or I will observe the state 1 with probability 1 by root 2 square. This 1 by root 2 square is the amplitude in front of the state 1, and the probability will be half. If I measure it in the plus minus basis, for that you have to represent psi in terms of the plus minus basis, that is the right hand side. So we will observe plus with probability. Once again, I take the amplitude of plus and I take the absolute value, I square it. Whatever the probability comes out, that will be the probability of observing plus. And whatever the probability comes out for if I take the absolute value of 1 minus I by 2, I square it, and that's the probability. So that will be the probability for observing minus. Okay. So now, so you can see that now suddenly this writing the same state in two different bases now has a meaning. I can measure a state, quantum state, in two different ways. In fact, there are infinitely many bases of a two-dimensional complex space. So which means there are infinitely many ways I can measure a quantum state. Okay, and each way of measuring a quantum state will give me different probability distributions. Okay, so there's one additional sort of important fact here. When I measure something, so suppose I'm measuring in 0 1 basis and I observe 0 with some probability. If I do observe 0, then the state of psi changes to 0. The state earlier was 1 by root 2 0 plus 1 by root 2 1. That state psi now suddenly changes to 0, or otherwise it's known as, in quantum computing language, it is known as this collapses. The state collapses to 0. Yeah, and similarly, if I do happen to observe 1 and observing 1 happens with probability half, the state once again changes to 1. So you see that the state of a quantum, the state of a qubit changes when I measure something. And that is quite a weird thing, and that is precisely the reason I faced a trouble when I was trying to figure out what was the state of B, because whenever I try to figure out if B equals to 0, whenever I run the line number 3, that is if B equal to 0, that I can only implement line number 3 by measuring the state B, and I measure state B and I get 0, then the state of the qubit B collapses to 0. So, at that point, the original state is completely lost. It is replaced by a state 0. This is something that is weird. Classical variables, I can check them, I can test their values infinitely many times, 1,000 times, and the values don't change. Whereas in quantum, quantum mechanics says this, that if I measure a qubit, the value changes depending on in what basis I am measuring. Okay, so that sort of causes a problem, which means that these sort of operations you cannot easily do. If you do, it's a destructive operation. If you check the state in this classical manner, if you apply a measurement, if you observe the value, then you suppose, the way you will implement is you will check the spin of the electron, or you will check the which path the photon is moving in. Once you do that, you change the state of the system. The qubit state changes. Whatever the original value the qubit was storing, that sort of goes away. So that makes things tricky. Okay, so just so remember this. So just to summarize, I've spoken about qubits, and just to summarize, so qubits have an intrinsic state which are not known to us always. That state is a continuum from continuum in a two-dimensional complex space, and when I observe the state collapses to, depending on in what basis I am observing, basically what instruments I am observing or in what mode I am observing, that depending on that will the state collapses, the state changes, and the observation only gives me partial information, because of the collapse, it only tells me whatever it collapsed to, and I don't get information about the part it did not collapse to. So just keep these things in mind, and you will be good. You will be able to figure out the rest of the lecture. Okay, so that was about qubit. So maybe at this point I'll just pause for a minute if there are any questions that I can answer at this point. Okay, then I'll go ahead. Okay, so that was about storing variables. Okay, so we learned what are the basic variables are. These are some analogous to bits, they're qubits. So now the next thing to write a program on a quantum computer, what you require are operations. You need to change the variables. So now let's first start with classical deterministic operations. So single bit deterministic operations, there are not many. There are only 4 of them, and they are not very interesting. So either I map 0 to 0 and 1 to 0, or I map 0 to 1 and 1 to 1. So these, in both the cases, the operation is essentially constant. Irrespective of the input, the left hand side always changes the value to 0. The second one, irrespective of the input, the variable value is changed to 1. The third one is simply flipping the bit. So if 0 becomes 1, 1 becomes 0. The fourth one doesn't do anything. It's a no operation. 0 remains 0, 1 remains 1. So classically, there are only 4 possible, and they are, as you can see, they are not very interesting. So if once you go into the slightly randomized domain, where you so we can have operations like, if you look at the left hand box, we can have operations something like this. If x equals to 0, then you set fx to be, suppose x is a variable. Initially it was 0. When I change the variable, I could change the variable x to I could change the variable x to 0 with probability half or 1 with probability half. And if the original value of x was 1, I could change the value of x to 0 with probability 1/3 or 1 with probability 2/3. So that's a valid operation on a single bit, a valid random operation on a single bit. And it's possible to represent this using a stochastic matrix. That is, if you treat the column vector, so I don't know what the value of x is, but as we saw earlier, that if x is a random bit, then I can represent x using column vectors. So now it is possible to get a column vector for the new value of x, and to get that value, I simply multiply the column vector for x. I left multiply it by something known as a stochastic matrix. So what you see is the stochastic matrix is half, 1/3, half, 2/3. It's a stochastic matrix, and once you multiply the whatever input, whatever was your column vector corresponding to x, initial corresponding to x, the initial values, then you multiply the column vector with the stochastic matrix. The new column vector you get will accurately represent the state of the new value of x. Okay, after you apply the random operations. Okay, so the takeaway message is randomized operations can be represented by multiplication with a stochastic matrix. Okay. Now let's go to qubit operations. So just a one-line analogy would be that multiplication, the qubit operations can be represented, one qubit operation can be represented by a multiplication of a state vector by a unitary matrix instead of a stochastic matrix, but by a unitary matrix. What is a unitary matrix? It is a L2 length preserving complex matrix. What is stochastic matrix? It is a L1 length preserving real matrix. Okay, so roughly things are sort of similar. Essentially, the same linear algebraic tools are being applied. And a very important sort of property that we will be using is the fact that a unitary matrix is a linear operation. We'll see what it means. Okay. Okay. So I have a, so I wanted to explain this qubit operations using an example. So what you see is something known as I mean, this is a one way to represent a quantum circuit. Okay. So on the left hand side, left of the vertical green line, you see two states, 0 and 0. You see two horizontal lines, those represent the two variables. So I have two quantum variables, two single qubit quantum variables. Okay, they are initialized to the state 0 and 0. Then what I do is I apply this H operation on the first qubit. Okay, so let's understand what the H operation does. Okay. So what the H operation is stands for something known as the Adamard gate. Okay, it is so given below. So that's the H operation. So what does the Adamard gate do? It changes if the qubit is in a state 0, it changes it to this state 1 by root 2 0 plus 1 by root 2 of 1. You have already seen these things before, so it should look familiar. That it's a complex combination of 1 by root 2 is the amplitude of state 0 and 1 by root 2 is the amplitude of the state 1 is the new state. If it is the state 1, if the input was state 1, then the output of the Adamard gate is 1 by root 2 0 minus 1 by root 2 1. So the amplitude of 0 is 1 by root 2 and amplitude of 1 is minus 1 by root 2. Now that is allowed because amplitudes can be complex numbers. Okay. But what does this mean? So we'll come to what does this mean later. Let's just do a quick exercise. What happens when I apply a Hadamard gate to, so let's take a state A0 plus B1. Remember, states are now complex combinations of the 0 and 1. So let's take an arbitrary state A0 plus B1 where A and B are arbitrary complex numbers with L2 norm equals to 1. So suppose I apply edge gate on it. What happens? Okay. So to know what happens, what you will do is you will use the fact that unitary operations are linear. So all quantum gates must be unitary. So H is a unitary operator, which means H is linear. So H is linear. That means that I can, to know the state, once I apply H, what I'll do is I'll apply H separately. Sorry. Okay. So I will apply H on A0 and I'll apply H on B1. H on A0, A is a scalar, so it comes out, which means what I do is I do A times H of 0 plus B times H of 1. Okay. And what is A times H of 0? H of 0 is given above. So it is 1 by root 2 0 plus 1 by root 2 1. So you do 1 by, I don't know how to write root 2 here. So I'll do something like this. Plus E 1 by root 2. Maybe I should write the entire thing just for the sake of completeness. 1 by root 2 1. 1 by root 2. So I'm simply now applying H on 0, whose operation is just given slightly above. So H on 1 is 1 minus 1 by root 2 0 minus 1 by root 2 1. So whatever you get after that, you simply add all of them up. what you will get is something like you just collect everything. So a by root 2 plus b by root 2 0 and whatever you get from 1. Okay, so you'll get a new state in which the amplitude of 0 will be a by root 2 plus b by root 2, and the amplitude of 1 will be a by root 2 minus b by root 2. So that's just the mathematics of applying the Hadamard gate. Okay. Okay, I need this one also. Okay, so okay, so we'll move forward. Then there is some more stuff happening, but there are some more notations here that I want to pinpoint. Okay, what is this? So the state here, the initial state was of the system. So this is now a 2-qubit system, right? So I have 2 qubits here. It was started with the initial state is this state 0 and 0. Okay, so now a shorthand for writing the so if I have 2 qubits in the state 0 and 0, I could write it a shorthand of this is just to write using in this manner, or which even more convenient notation is to just sort of club both of them together. But what does this mean? Remember, 0 represented the column vector 1 0. So when I am putting 2 zeros at the side by side, when I'm saying that it's a combination, now it says 2 qubits each in the state 0, it is something known as a tensor. It's essentially mathematically a tensor product of 2 column vectors. So those of you who are familiar with tensor product will remember this, will see this immediately, that a tensor product of 1 0 1 0 is essentially another column vector. But those of you who don't, it's not important. So there is an equivalent mathematical vectorial representation of this initial state 2 qubit state 0 0. It is going to be a 4-dimensional complex space. Okay, so this should not like completely scare you, because all I'm doing is I'm simply doing something equivalent to the code that you see roughly on the left, this part, where I have 2 variables b1 and b2, both are in 0, and then I create a pair of them. So this is like something in Python we have a concept of, there's a concept of creating tuples. In many programming languages that you can create tuples. So it's like I'm creating a tuple. I'm creating a pair of I'm creating a new variable which is a pair of 2 variables. Okay, and from in that pair I'm randomizing, I'm approaching this H operator, you will see slightly later, that is similar to a randomized operation where I randomly make it 0 or 1. Okay, so then I'm randomizing the b1, and the state of the circuit, the state of the system after I applied the H is like I have a pair of qubits, one of which is a random is something like a random bit, and the second is a bit that is initialized to 0. Okay, so the state of the qubit, so state of the quantum circuit after, so this is how a quantum circuit looks like, what you see in the picture. Okay, I have qubits, and then I have the lines, the horizontal lines represent the variables, the qubits, and then I have blocks which represent the gates on them. Okay, so the state after the state of the this 2 qubit system after applying the H gate is the first qubit is in the state 1 by root 2, 0 plus 1, and the second is in the state 0. So the entire state is 0 0 plus 1 0 with a variable 1 by root 2. My this writing is getting not proper because of something wrong with the software, but this it's 0 0 plus 1 0 with a normalization factor 1 by root 2 outside. Okay, and okay, so that's the state after H. Now there is this funny symbol which we'll analyze next. Okay, so this part enclosed by a red. So what is this red circle? This red operation, it seems like it's a 2 qubit operation because it is acting on 2 qubits. Indeed, and it is known as the controlled NOT gate or the CNOT gate. Okay, so the controlled NOT, it's one. So this H gate and the controlled NOT gate are the 2 most used operations in quantum circuits. So this quantum NOT gate, what it does is it acts. So these acts on 2 qubits. Okay, so the operation on the basis states are given below. So operation on 0 0, what it does on 0 0, if the input the state of the first qubit is 0, the second qubit is 0, then it doesn't do anything. It keeps them unchanged. The state remains 0 and 0. If the state of the first qubit is 0, second is 1, again it does nothing to the qubits. The state remains as it is, 0, 1. However, if the state of the first qubit is 1, then it flips the second qubit. So the second qubit was 0, it now becomes 1. If the second qubit was 1, it now becomes 0. Okay, so that's how a control NOT gate behaves. However, a state of this 2-qubit system could be anything. It need not be the 0, 0, 0, 1. It need not be one of those 4 values. It could be anything. For example, imagine I have an arbitrary state where A and B are some complex number, and I have some state A 0, 0 plus B 1, 0. What happens if I apply C naught on that? Okay, so once again, we will use the fact that unitary operations, C naught is a unitary operation. All quantum gates are unitary operations. So they are linear, which means to know the value of C naught, to know the value of the 2 qubits, to know the state of the 2 qubits after applying C naught, what we will do is we will apply C naughts individually to them. So I'll apply A on 0, 0, and I'll apply on B of 1, 0. So how do I compute this? So C naught of so A is a scalar, so it comes out. So I get A of C naught on 0, 0 plus B of C naught on 1, 0. That's the beauty of things being linear. You can just simply apply them, just go inside the plus. Okay, and A of C naught 0, 0 is given above. It is 0, 0, and B of C naught 1, 0 is also given above. So it is B of 1, 1. The state that I get is now a combination of 0, 0 and 1, 1. Okay, what does that mean? We will come there. But at least mathematically, you should be now able to calculate the state just by moving from left to right, applying one gate after the other. Okay, so as you can see, what I'm trying to convince you is that if I tell you the action of gates on the basis states, then it is possible for you to dry run the circuit on any input. You simply have to apply them linearly. Even if the state is a combination of 2 basis states, you apply them linearly on each combination and you add them up. Okay, and we get that because everything is a vector and unitary matrix is a linear operation. Okay, so what is the circuit doing? So what it is doing is, notice the box. Pay attention to the box on the left. Okay, so I have 2 variables B1, B2. So B1, so okay, so until this, let's see if I can draw a line. Oops. Until this line we had done earlier, so we created so the state of the system was something like a pair of two variables B1, B2. Now the third gate, what you are now observe what does the C naught gate do? If the first bit is 0, it does nothing. If the first bit is 1, it simply applies a Boolean NOT operator, or in other words, we can say that it simply subtracts the value from 1. So I say something like this, that the state of the system after the C naught gate is something like this pair 3, which is a pair of B1, B2, where B1 remains whatever it was earlier, and B2 changes its value depending on the value of B1. If B1 is 0, B2 doesn't change. If B1 is 1, then B2 is flipped. If B2 was 0, it becomes 1. If B2 was 1, it becomes 0. Okay. So that's roughly what sort of a classical analogy of the quantum circuit that you see here. Right. So far it seems that whatever we could do classical quantum, we can also write a classical code for it. Okay. So let's see where things may change. Okay. So okay. Now let's try to understand what does it. So we had earlier I had told you what does it mean to have a what is the value of a single qubit state, right? It depends on the measurement. And similarly here I have a 2-qubit state. So what is the value of this 2-qubit state? What do I do with I should get a 2-qubit state after running the circuit. What do I do with the thing? So I'll suppose I observe it. Okay, so if I observe this, once again you have to ask me what basis I observe it in, and so I'll use the 0, 1 basis. Okay, so now there are some little bit of mathematics that I'm missing out, that I'm leaving out. So if you apply, so I haven't told you how to measure in a 2-qubit basis. So those are things are there. So if I measure in 2-qubit basis, that's essentially so measuring in the 0, 0, 0, 1, 1, 1, and 1, 0 basis, what we will get is we will see that we will see that the output is either 0, 0 with probability half. So the first we will either observe both the qubits in the state 0, 0, or we will observe both the qubits in the state 1, 1 with equal probability. So the funny part here to observe is the first and 2 qubits are always going to be the same. If the first qubit is in the state 0, the second qubit is also going to be in the state 0. If the first qubit is in the state 1, the second qubit is also going to be in the state 1. Now, this curious fact that both the qubits have the same value, this fact is known as entanglement. The values, the states of the 2 qubits are now entangled. So it's like both of them acquire the same value in some sense. This should not appear as very surprising here, because even in the classical case, the box that you see on the left, the value of B1, B2 will always be the same. Okay. Right. So you can sort of you can work the things out. Okay. So this is what an entanglement what an entanglement is, that when values of 2 qubits are sort of they are dependent on each other in this way, which is also possible for classically. We can have dependent random variables. So now let's try to see something very funny about a very sort of a magical thing that has no classical analogy. Okay. So look at the circuit, the small sort of operation that I have on the left side. Okay. So I have it's a single qubit system. I initialize it with the state 0, and I apply the operation, Hadamard operation, the H operation. What do I get? As before, I had shown that I get the state plus, and I showed you how do I compute the action of H on any arbitrary state. So you can apply that on the plus state, and you will see that it turns out that the state remains 0. Okay, so what do I get here? I have a single qubit. I apply H, I get the state plus. Then I apply H again, I get the state 0. Okay, so what's so magical about it? Okay, so suppose instead of applying the second H, I had observed the plus state. What would I have obtained? So plus is plus can be written as 1 by root 2 0 plus 1 by root 2 1, and we did this exercise earlier. We would have observed 0 with probability half and 1 with probability half. Okay, now suppose that this plus was actually a randomly chosen state from 0 and 1 with equal probability. Okay, so for a moment, suppose that plus is a state that is either 0 or 1 with equal probability. Then which basically means H, when I applied it on 0, so now I know what is the action of H on 0, and now I know what is the action of H on 1, and plus is I'm assuming that plus is either 0 or 1 with equal probability. So if you now do the calculations, you can figure out, you will see that after you apply the second H gate, you will see that the probability of observing 0 is going to be half. The probability of observing 1 is going to be half. That is, you will be getting both 0, 1, 1 with equal probability. But that's not what we see here. After we apply the second H gate, we see that the state of the system, the single qubit, is always in the state 0. Whereas if plus was actually a randomly chosen state from 0 or 1, then it would have been then after the second H gate, it would have been once again a randomly chosen state from 0 and 1. Okay, which means that plus is not a randomly chosen state from 0 and 1. It is not like a classical bit, classical random bit, that is, it is either 0 or 1 with half and half probability. It is in fact both 0 and 1 in some sense. So this is what is known as a superposition. And superposition is a combination of two states, but not an OR combination. It's in a sense, it is both 0 and 1 in some sense. Okay, it is difficult to explain this idea of and because we are not familiar with one. We are not familiar with with something having two different colors at the same time. Okay, so but when we go to quantum level, so unless we observe particles or quantum level particles can have two different properties at the same time. So that is exactly what is happening here. And I'm just trying to convince you that plus is not a or state, it's an and state. It is something like it is both 0 and 1. And this is what sort of so we have seen the two facts, entanglement and superposition. These are the two crucial ingredients which allow us to do things better than classical. Okay, so just to summarize, what I discussed are state evolution operations which specify the action. You only need to specify the action only on basis states, and for all the other states, one can linearly extrapolate the action on the basis states. Okay, and there's another property that I should mention here, that the actions are all unitary. And unitary operations are reversible, which means state evolutions are reversible. That is, if I tell you the state at any point, you would be able to compute what was the state somewhere before. Okay, measurement is not a unitary operation. So once things measure, once we do a measurement or observation, things collapse. So that is not reversible. But all the other gates, etc., they're all reversible, which has a very curious side effect. It means that, so this is you see in the block a standard regular code. Okay, and we routinely use the fact, we use statements like I set a variable. So here you see that I am setting arj to be equal to arj plus 1 without caring whatever the value of what the value of arj was before, right? So after that square box is executed, at that point, if I tell you the value of arj, you will not be able to figure out what was the value of j before the box was being executed, because the value is lost. But this is a very routine thing to do. We frequently set variables. This is something we cannot do anymore when I'm writing a quantum code, because quantum operations must be reversible, and this is a non-reversible process. Okay, so you have to be careful. There's no way around it. This is a quantum mechanical limitation, and so there's no, and so we have to sort of adjust to it and implement things which does not involve irreversible operations. It also means that we cannot create copies of a qubit. Okay, so frequently we write things like variable. We have a variable b, and we say that variable c equals to variable b. Now that is also not possible. We cannot create arbitrary copies of arbitrary states. And why? And the reason, once again, is because this operation is again a non-linear operation, which is why we cannot. It's not possible in quantum mechanics. Okay, so I have told you what qubits are. I've told you how do I do evolution of states? How do I change states of qubits? Okay, so now let's talk about briefly about a very simple operation, a very simple operation at the core of very complicated algorithms. Just simple problem of searching. So imagine I have a binary array of size 100. Okay, and the challenge is to find any index I. So it's a binary array only with zeros and ones. So the question is to find any I for which ai equals to 1. So I need to find, I need to find any position at which the value is 1. Okay. And what am I going to count? And obviously one way of doing it is I start by checking A1. If I get 1, good, I stop and I output 1. Otherwise I check A2. If I get 1, I stop and I output 2. Otherwise I check A3 and I do it linearly, right? You can see that it's going to take, in the worst case, I need to make 100 probes to the array. So I will count the number of probes I need. So let's look at a randomized process of doing it, and it's a very trivial randomized process. I have a variable b which is randomly chosen from 1 to 100. And so what does b mean? Therefore, it means that b is 1 with probability 0.01, b is 2 with probability 0.01, and so on and so forth, and b is 100 with probability 0.01. So b is some value from 1 to 100 with 0.01. And then I get the value of a at the position b, and if the value of and I store it in C, and then if the value is 1, then I have found a position and I output B. Otherwise, say I don't find it. Okay, so this entire thing simply makes one probe to A is only one probe it is making, just calling A at one position, and the success probability. Suppose M is a number of ones in A, then the probability of success is very easy to, which is elementary probability. You can compute that the probability, this algorithm will find a good I with probability M by 100. Okay, so if there are 10 A's, 10 positions at which A is 1, then the probability will be 1 by 10th. Okay. So the probability is very low. What we can do is we can run this block of code k times, and if any time I get a B, so if I run it once, if I get not found, I run it again. If I run it 10 times, if I get not found in all 10 times, I say okay, I have not found anything. Otherwise, if at any iteration I found a position B, I simply stop at that one and output that particular B. So you can do some elementary, probability, and you'll see that if I roughly call this block of code on the left that you see, the block, if I roughly call it 100 by M times, then I will be able to find I, provided one such I is there, a good I is there, with probability nearly close to 1. So with success probability, I will be reasonably successful in finding a good I if I choose the number of iterations of this block of code 100 by M, which basically means, and each block of code is only making one probe to A, which means with about 100 by M probes to A, I can get a very high success probability. Okay, so let's look at an equivalent quantum operation of doing it. So for that, I need a way to probe this A. Okay, so now I will define a gate to make this probes. I'll define a UA gate on 2 registers. Okay, now what are registers? Registers are combinations of qubits. Okay, so I have a 10 qubit register, I call it register 1, which stores the position, and a 1 qubit register 2, which stores the value. And I create this I create this UA gate that you see here. Okay, so what this gate does is, if it takes 2 registers, and the first register stores the P and the second register stores a value, and what it does, it stores the value of A at this position P in the second register. If the second register was initialized to 0, it stores the value as it is. If the second register was initialized to 1, it flips the value. And why do I am doing this flipping thing? Just to make this entire process reversible, because quantum operations have to be reversible. So notice that this operation makes only one probe to A. Okay, so now come to the next statement. Now I create, we have already seen how do I create these single qubit superpositions. Okay, now I can extend this idea and I can create a superposition over 100 possible positions. So this is a uniform superposition over 100 possible positions. So P is now, okay, so first register contains this first register is in this state, which is a uniform superposition over 100 possible positions. What happens when I apply, what happens when I add a second qubit initialized to 0 to it and apply UA on it? Well, we have seen that it's easy to do these things because UA is a linear operator. So I'll simply apply them linearly. So once you apply linearly this operator on each of the individual states in the superposition, you see what we get is a uniform superposition of the following kind. The first register is in 1 and second register is in A1. First register is in 2, second is in A2, first is in 3, second is in A3, and so on and so forth. Okay, so this this particular state, is what I will get when I apply the UA gate on this B and a 0. Okay, so if I at this point, if I make an observation on, if I measure this state, what I will get is I will get any B and AB with probability 1 by 100. Right. So this is similar to the randomized process that we saw earlier. That is, I get a random B. And the value of A at that particular B with probability 1 by 100. So this is 100. This is I made this is a typo. Sorry. This is 1 by 100. Okay. So this is no better than classical. So what did we achieve? Okay. So what Locke Grover what he observed is that suppose I don't observe it, don't measure at this point, and then he devised a somewhat a very clever algorithm, which basically allowed us the following thing. In the classical case, we had to make 100 by m probes to we have to make 100 by m probes to get a constant probability. His technique gives us a constant success probability using square root of 100 by m probes. Okay, so if m was, let's say, 1, then in the earlier case, earlier algorithm, we would roughly need 100 probes, where in this case I would need 10 probes to A. Okay, so that this algorithm is known as the Grover search algorithm, and what it does is, in a nutshell, if something requires order of n squared to search, then, or if something requires order of t to search classically, then Grover search algorithm often gives you a square root speed up. That is, it allows you to search in square root t, order square root t many steps. Okay, so that is the beauty of Grover search algorithm, and this algorithm has been used as a subroutine to construct many more sophisticated algorithms. So as in itself is not a very sophisticated thing, because Google or SQL databases, they don't really search in an array, they have indexes on it. But it turns out that you can use this Grover search as a subroutine in many, in many complicated algorithms, because all complicated algorithms at some point require searching over some things, linear searches, and that you can now efficiently do using Grover search and get a square root speed. Okay, so that was, I just wanted to give you a glimpse of how these algorithms are designed and where do they slightly start differing from and improving upon classical. Okay, so this is just a sort of a one slide showing that these, whatever I am saying here, are not completely just a theoretical thing. You can actually program, you can only construct the circuits. Early days, people used to construct circuit using Boolean logic gates. That was really in like 50s and 60s, and now even so, we are in a way somewhere close to that level right these days. So we have many platforms now. IBM as a platform and Rigetti as a platform. There are a lot of platforms where you can construct quantum circuits by building putting gates on qubits. And you have seen this kind of in this talk. I tried to give you an idea of how to analyze these sort of circuits, and these platforms often also have high level programming language that allows you to sort of use not use a GUI to drag and drop, which would be very cumbersome to create a large circuit, but to use high level language libraries, Python, and even higher level C# and higher level libraries to construct circuits. And they even have wrappers to run Grover search and more complicated sort of quantum algorithms. Okay. So just to sort of, I have about 10 minutes left, so I'll wanted to show you some sort of very advanced things that you can do once you start with this quantum computing. What are the sort of the cutting edge things that have been done? So this is a circuit for a linear system of equations. Okay, so what does this do? So suppose I have a linear system of equations, Ax equals to b, where I have n equations. So classical technique for solving it, the best known is conjugate gradient descent, which roughly requires order n steps. Okay, there sort of not recently, roughly about 10 years back, an algorithm was given by Harrow, Hasidim, and Lloyd, which required order log n steps. Now, both algorithms don't do the exact same things, but nevertheless, this order log n algorithm was fairly a very strong improvement over whatever we can do classically. There are some sort of catches there, so how useful it is, it's not immediately clear, but this is still nevertheless a very strong improvement, right? Okay. So you can solve. So once you know how to solve linear system of equations, suddenly a lot of things sort of comes into place, because a lot of optimization essentially can be modeled as solving linear system of equations. Okay. This is another sort of cutting edge sort of technique. This is known as the variational quantum ion solver. What it's used for, it is used to obtain the ion values and ion vectors of an operator. So if I have an operator, I want to compute this ion value, and ion vector, and there is the best classical method is suppose the operator is n dimensional, then the best classical method requires polynomial in n many steps. The variational ion solver is what it does is essentially you have a circuit in the beginning, the red part, the red part, which is a circuit that you see in the bottom, some circuit like this. You observe that the circuit at the bottom has these gates which are parameterized by these angles, theta 1, theta 2, theta 3, and so on and so forth. So these gates are parameterized. So the general idea is that you start with a circuit like this, you apply it on a state, and then you observe its measurement. You observe this output, you measure it, and then you find out based on the measurement, you sort of do some sort of a gradient descent, and you find out a new set of parameters, theta 1, theta 2, and theta, all those 9 parameters, theta 9, and then you update, then you construct a new circuit with the new parameters, and you again run the circuit on the same state, all the zeros, you measure it once again, and you again do a gradient descent to optimize the parameters. So you keep on doing this and until the parameters converge. So it's again becomes a parameter optimization, and this technique is known as variational quantum ion solver. Then there is this technique called quantum approximate optimization algorithmic technique, where what it's used for, it is used for to solve optimization problems, but not in the linear optimization manner. So once again, here what happens is there are these blocks of these blue blocks and this yellow blocks. These blue blocks encode the objective function of the optimization function of the optimization problem, and the orange blocks are some sort of mixing among the different sort of paths. And these you observe these gamma 1 and beta 1 parameters. These are parameters that are used in the gates constructed that are used in these blocks. And so the idea is same as before. You run the circuit once, you measure it, and then you run a classical optimization solver where you optimize the gamma and the beta parameters, and then you change your circuit. You construct, now you use the new set of parameters to have new sets of gates, and you keep on running this loop until the parameters converge. And that's the quantum approximate optimization algorithms. QAOA is the buzzword there. VQE is the buzzword here, is the short form here. Okay. Then we have the quantum neural network, where so the bottom right picture is from the quantum TensorFlow, which was announced by Google early this year, in somewhere around March. The top is a picture from a neural network that was used for, I think, doing portfolio optimization, for a finance portfolio optimization. So the ideas are again similar. You have input qubits coming in, and you have gates that are applied. You see that these gates, I'll zoom in a bit. You see the gates are theta 1, r theta 2. They are again parameterized by theta 1. And then you have an input layer, you have a hidden layer, and you have an output layer as usual in a neural network. Then you get the output, and then you do back propagation to learn the better theta is, and then you sort of keep on doing these things. The similar sort of ideas, but it's all, you can see that all the last three that I spoke about are in that learning framework. You learn the right parameters. Okay, this is slightly a different technique. It's known as quantum annealing. Okay, so here what happens is if you are familiar with simulated annealing, then this will probably make sense. So here you are doing, or even Monte Carlo simulation, then this will make sense. You are doing a Monte Carlo simulation kind of thing. You are trying to find out the objective, the optimum value of an objective function. So the objective function optimum value is here. And what happens in a gradient descent is it's likely that you get stuck in local optima. So this is another local optima. So you get stuck here. So in quantum annealing, what it allows you is, the beauty is that there is something known as quantum tunneling, which allows you to sort of move past the barrier. So this hill that you see between these two optimum, so this is the barrier, and this quantum mechanics allows you to sort of move past the this barrier. The phenomenon is known as tunneling. So that allows you to sort of not get stuck in local optimum, and instead move towards global optima. Right. This is motivated from a classical approach known as simulated annealing. In simulated annealing, you get past these barriers by using thermal jumps, whereas in quantum annealing, you get past the barriers by doing quantum tunneling. Okay, the techniques and the mathematics here are fairly different, but the quantum annealing is the technique that is used by the D-wave quantum computer. That's so there are two sort of so this is the D-wave quantum computer. The other classes of quantum computers that are commercially available are by IBM, Rigetti, and Google has one. It's not available to the masses, but they are all based on the gate model that I was showing here. These are all of the gate model where you create gates to construct solve a problem, can construct a circuit using gates. Whereas annealing, it's a slightly a different way of solving it. The idea is this. Okay, what are some of the problems that people have solved using these sort of advanced techniques? So D-Wave has shown how to do portfolio optimization. This is finance portfolio. You have a portfolio of stocks and mutual funds and assets. So how do I optimize portfolios? Google has shown how to simulate hydrogen molecule. Simulating hydrogen molecules are again, it's a toy problem. People really want to simulate more complicated molecules with like thousands of atoms, but at least there is now something to start with. So yeah, so we know how to do this. So right now we know how to. I think after hydrogen, some two atom molecule was also simulated. I don't forget the name of the chemical. Then Volkswagen and Google have also done optimization for traffic. I think over traffic of Seattle is what they optimized, and then material structure for e-vehicle battery. So this is all sort of done. So there are some, these are so but you should understand that these are all mostly proof of concept, because none of them are at production scale. These are not at the scale where they are really immediately useful. So it is not immediately clear what is the killer application for quantum computing. And so that's where I would end the talk with, that the killer application is still left. And I hope some of you will get interested and hopefully will get involved in solving the first real problem of using a quantum computer. So on the chart above, you see sort of the rough progress and the companies that are in this space. You can see there are a lot of companies. This is a chart that I took that ends in 2015. This is 2020. So there are a lot more companies there. It doesn't show the only Indian company in that space. So there is an Indian company in Bangalore. There's only one Indian company that doesn't work on quantum computing. It works on quantum cryptography. But there's still at least on the global map, India still has a place there. But there are now a lot more companies and a lot more players there. A lot of startups are also there. So that's where I'll end. And thank you very much for listening. And I guess there are now some time for questions.
So yes, sir, I have a question.
Yes. Yeah.
Yes, sir. You said there is a neural network implementation in quantum computing. So
Yes.
can we have equivalent to classical neural networks, or we can test any algorithm, any classification on this platform, sir?
Yes. So if you so Google has released a TensorFlow for quantum, where you can try out classical problems. That is, suppose you want to do image segmentation, classification, something to do with documents, etc. You can try out those things. And there's another platform known as by PennyLane. So that also has frameworks available for doing basically machine learning problems. So you can use those platforms for trying out your standard classification, regression, etc. Sort of these sort of things.
IBM also supports, sir.
IBM also, yes,
Cloud.
IBM or Qiskit, they have a library where they also have implemented some of them. I don't know how mature they are, because IBM is trying to look at the entire ecosystem, from normal Grover's kind of algorithms to these and every kind, all kind of things. So yes, I don't know what is the state there, like how good are they, but I know for sure that when people talk about implementing these machine learning algorithms on quantum platform, I'm talking about real quantum platforms, not simulation, then they usually talk about TensorFlow or PennyLane.
Okay,
but I think quantum was, yes, go ahead.
Google platform is a right one to test our algorithms.
Yes, it's a good one. At least that's what my students, that's what I heard. Though I don't really work on those things. This is what I've just heard from people and whatever I've read on blogs. But these are the two sort of well-known entities, Penny Lane and Google. Penny Lane,
Yes.
PENNYLANE, Penny Lane.
Yeah, Penny. Yes, sir. My second question was like part of the first question only. The library support, as you said, I think it's available on Google platform like TensorFlow, what it supports. API for. Yes, sir.
Yeah. So I have not checked them out personally, but I know there are supports available, and I know a lot of people are trying out these sort of things. They are trying out toy, code for writing toy simulation, etc. So on GitHub, you will find lots of code that runs on these platforms.
Yes, sir. Thank you so much, sir. Thank you, sir.
Participants, any other questions?
Yeah.
Sir, I have another question.
Yes. Go ahead.
Actually, I think the same doubt was there for me. The quantum state is represented as a vector, sir. Actually,
Mathematically represented as a vector, right?
vector. So I want like some interpretation, like how exactly the state is a vector in Hilbert space, as you said.
I did not understand your question. What do you mean by how exactly?
State, like for example, classical, they say that state is 0, state is 1.
Right.
We have clear like discrimination between the state 0 and 1 here.
Right.
It is a binary.
Right.
My question is like in quantum computing, the quantum state or a qubit state is represented as a vector.
Right.
As we are so far we are using 1 0 a column vector for 0 state and 0 1 for state 1.
Right.
How exactly it is a like vector? Why it is so? That is like
So the answer to why is easy because quantum mechanics told us so. Okay, so we don't know what the reality is. It's just that the predictions of quantum mechanics have been fairly consistent. So we trust its mathematics. Okay, so quantum mechanics tells us that the states should be treated as complex vectors in this complex space. Now, how it is? So if you have an arbitrary state, so an arbitrary state would look something like this. Okay, which is a mixture of a superposition of two states. And so if you can, so I think I answered your second question, but your first question, I'm still not clear what your first question is. So maybe with this example, can you once again restate your first question?
yes, that is how it is mathematically as a vector state of any system.
Okay, so I tried to convince you that even a normal regular bit is also can be represented as a vector.
Okay.
It's not a very helpful way of doing it. It's sort of cumbersome, but it can be done. Okay, so here quantum mechanics tells us that you can analyze quantum mechanical systems using vectors, and so it is sort of the preferred way of analyzing sort of quantum computing. However, if you are willing to trust the fundamentals, then you can simply forget even the vector. In fact, most quantum computing lecture notes or lectures, you will only see the vector representation only in the first lecture. Second lecture onwards, you will not even see the vector representation. You will straight away only use this angular bracket notations, this bracket, this notations. Yes. Right. So the vector representation is something only to keep at the back of your mind, but you can do the entire field without even knowing, fully understanding, or without that it is fully a vector. Yes, so you don't need to know that it's a vector, but yes, if you want to really understand what goes at the back of it, then this is what it is.
Thank you, sir. Thank you so much, sir. Yes, sir. I got it.
Any questions from the participants? Any questions from the participants? I think no questions, sir.
Okay, okay, fair enough.
Okay.
Okay.
Okay, sir. I request. Okay, sir. I request Mr. Sairam sir to propose vote of thanks.
Respected organizers, Dr. Mukul sir and Mr. B. Dhanraj, and our most valued guests, it's my privilege to have been asked to propose a vote of thanks on this occasion. I, on behalf of Vadhavan College of Engineering and the entire sponsoring organization, crew, special guests, and on my own behalf, extend my hearty vote of thanks to the speaker for gracing his important work and sharing with us his findings and opinions for today. A big thank you to Mr. Beira Garu for his quantum computing. I must mention our deep sense of appreciation for his explanation on mathematical representation of qubit system. And our sincere thanks for giving an excellent coverage to state evaluation, operation of qubit. I'm further grateful for demonstrating a problem of searching which made understanding more clear, and the cutting edge solvers like optimization techniques, variational quantum eigensolvers, quantum approval optimization. I'm also very grateful for his analysis. We are all inspired by your great work in quantum computing, sir. Finally, I would like to take this opportunity to place on record our hearty thanks to management, Vadhavan College of Engineering, principal, and our HOD, Mr. Rao sir, for extending his support and guidance in all the occasions. Well, ladies and gentlemen, an event this cannot happen overnight. With the continuous support from our organizers, Mr. Dhanraj and Mr. Mukul sir, and my dear colleagues, we thank our beloved speaker for being with us this morning. It's been a great pleasure, sir. Thank you very much for your speech. Thank you, sir.
Thank you all. Thank you for inviting me, and thank you for giving the time. Okay.
Thank you, Professor. Thank you very much.
Thank you.
Thank you, sir.
Sir, Dhanraj sir. Hello? Hello? Hello, sir. This is participant, sir. Hello? Hello?
Hello, sir. Yes, sir. Tell me, sir.
Yes, sir. Can you share the presentation, sir? PPT?
Okay.
Person. Yes, sir. That is required.
Okay, sir. That is, I mean, this presentation, sir, or the coming session? You want me to share?
This presentation, sir, PPT of this session. Yes, sir.
Sure, sir. I will put a request. Okay.
Thank you, sir. Thank you, sir.
Thank you so much. Thank you so much. Okay, I request all the participants can leave the session. So afternoon session link will be shared within 5 to 10 minutes. So kindly give your feedback for the morning session. Thank you so much.